Good morning, Professor. Okay, welcome everybody. I hope your break was good. Did anybody do anything special? Nothing? Okay. Okay. So I hope that everyone saw the message about our test next week. So we're having a test on chapter 11, and it's going to be an oral test, which and the way what I mean is we're going to I'll have a individual discussion with each person separately, where I'll just ask you questions about the text, and then you'll respond to them, and everybody else will it'll be a separate room. So we'll do it that way. And since we have about 10 people, that'll take about most of our class, actually. So anyway, that's and I made a bunch of videos to explain chapter 11, and so I recommend that you watch the video, then you read the text, then you answer the questions, then you read the text again, because it's going to be, I could ask you small details about the text, so you need to understand it very well. And the reason is that this chapter is the precursor for all the rest of the neural deep learning that we do. So you need to know this basically inside out, so that we can cover all the neural network after this. Now, hopefully, we'll get to the convolutional neural network in time before the end of the semester. So if we do that, then we will have built a neural network that is was modern about 7 years ago. I mean, it was cutting edge 7 years ago. It's still very important, but it was the very peak of cutting edge 7 years ago about. So it's very up to date. So if we get that far, it'll be great. But anyway, we are going to do the test on chapter 11 next week. Okay, but you really need to know it almost you need to memorize it, which is a lot to do. So so anyway, you have the videos to work with, and you have the text to work with. Now, I'm just going to continue with where we were last week, even though it's covered in the video, because I can't really go anywhere else. Can't go to new material. So I'm going to continue with that. So let me share my screen. Does anybody have any questions before we start? Why can't I? Something's not working. Why can't I blow up my screen here? Let's see. I can't make this any bigger. Why is that? If I use scrolling, I can't blow it up. How can I do it otherwise? Here. Okay. Okay. Okay, does anybody have any questions before we start? All right. So just here's what we were working on last time. We were working on chapter 11, which is to build a neural network. And we were going to work with 3 separate designs. This would be the simplest one, or the simplest architecture. And this is a little bit less simple because we have 2 nodes here. And then here's a more general one. Now, neural networks will have more. Here we have 3 levels. And neural networks always have at least the input level and the output level and at least 1 hidden layer. But they can have many more than just 1 hidden layer. This is called a hidden layer. Anything other than the input and the output is called a hidden layer, because this is not really hidden because it receives the outside data, and this is not really hidden because it sends data outside to the user. So, but this is hidden. So, but there can be many hidden layers, and there can be many nodes in each hidden layer. You could have like 1,000 nodes in a hidden layer. That wouldn't be unusual. But math and everything is still the same. It's just you just create it. It's really the same. So we don't need to, of course, work with 1,000. We can just work with 3. And here, this represents the inputs to your problem. So if you're trying to predict, for example, the stock price, this might be some information about stocks. So like, what was the volume of stock traded yesterday? And what was the price yesterday? And from those 2 numbers, you might predict the price today. Okay, so you'd have 2 inputs here, and then you'd predict something out here. And for our neural networks, well, for now, the neural networks we're going to work with are predicting a number out here, although the last chapter is not. The last chapter is doing image recognition and predicting whether a handwritten digit is a 1, a 2, a 3, a 4, and so on. Okay, so we discussed the way the subscripts are, and we said that when we have a W23 here, that's going to mean for us that the weight, this is the weight, and that the weight or the edge originates in a node labeled 2 here, so W2, and goes to a node with a 3 here, so W2, 3. And these numbers here, 2, 2, 2, 2, 2, 2, 3, 3, indicate the layer. So these are all things in layer 2, and these are all things in layer 3. And here we could call this A1 and A2. In other words, an A, we could call it A1, A11. That would mean it's in the first layer, and this would be A2. I'm sorry, A1, 1. Sorry, A1, 2. Sorry. So that would mean that this is in layer 1, and it's the second node. So, but usually we'll call this X because it's typically it's, of course, we usually use X for the inputs. So we don't usually use A here, but we could. A is here, and A is also here. Now, since this is the last one, we also use, instead of A3, we call it Y hat. Okay, because it's actually our prediction, right? Besides being the third, in the third layer, it's also our prediction. So we'll sometimes use A31, or sometimes we'll use Y hat. So and typically we'll use actually Y hat, but either one can be used. Okay, and then and we discussed how to calculate these values. So just to review, to get Z1 here, I'm sorry, Z21, we take this value times this value plus this value times, where's it? It's, this is 2,1, where's 2,1 here? Times this value. Okay, so we do this times that, this times that, and then we add them. And that gives us this. Okay, and then we do something similar for these. Now we have to say what we mean by these numbers. And these numbers are just, remember this, we said that we have, we're going to be working with a sigmoid function, which looks like that. This is 0. And this height is 1/2 there. And it goes as, it never reaches the height of 1, and it never reaches the height of 0. Anyway, so that we put this number into this function. So for example, if Z1 was over here, this is where that Z1 calculation, Z11 was, then we put that into the sigmoid function, we'd get a height like this. So we get this value out. We just put this Z1 into the sigmoid function, and we get something out. We put this in, we get something out, and so on. And then we do the same process again, where we take this times this, and this times this, and this times this, and add those products up to get this. So we add them up, and we get this. And then we take this and we put it into sigma, and we get out, I'm sorry, we take this and we put it into sigma, and we get out this. So that's the calculations that we're doing. And the thing is that if we didn't have, let's go back to this one. If we didn't do this, and we didn't do the same thing here, put it Z3 into sigma, then this whole process would just be a linear function. Because if you look at this, what would it be? It would be, we take x times w, right? And that gives us z. And then if we didn't do this part, then we would have times w2. Sorry, this would be w1, and this would be w2, and that would give us this. And then we just get the then our output would just be this. And this is just that if we think of x as the input and these two as constants, this is just, x or k times x. A constant times x, which is just a linear function. And that's if we're trying to model the stock market with linear, that means we think that when we put in the volume, suppose this is volume, and this is the price tomorrow, and we have to use the formula like this, it means it has to be, in this case, it can't even be, it has to go through 0, and it has to be like that. Now, it's not likely that when you take the the volume, that if the volume is more, it's going to be linear, right? We don't expect that the price is a linear function of the volume. That would be very, very restrictive, right? We don't want to be stuck with that kind of restriction. So we don't want to have just linear. So that's basically the reason why we do this f, or we do the sigmoid function part. That allows the shape to be much more flexible. We have a combination of linear and sigmoid. You can get all kinds of crazy curves to represent the relationship between the input and the output, or it could be the inputs and the outputs. So we don't, so that's basically why we do this. Okay, so now we can say here's a Z2, we put Z2 into F, we get A2, we put A2, we multiply times W2, here A2 times W2. This is just the linear, I'm sorry, just the 1, 1, 1 case. So A2 times W2 gives us Z3, and then we put that into Y hat. So now we have Y hat. We can say it's F of Z3, but of course Z3 is this, so we can say that it's I'm sorry, and this part here is this, so we can write A2 as this times W2, so we have that, and sorry, and Z2 is this, so we can write it like this. F of X W1, that's the F of this, which is A2, times W2, and then we take F of that. So we can write it Y hat like this. And when we write it like this, we see that Y hat is a function of both X1 and X2, right? It's a function of both X1 and X2. So our prediction is a function of both of those. Okay, now we define the error, and what we mean by the error is Y minus Y hat. So it's our prediction, the difference between our prediction and the actual true value. So we're assuming that we have labeled data to train our neural network on. So we're assuming, like, we know the price versus the volume for much of our data. So like we look at the past data, and it's easy to find, you look at a stock, you can find what was its price today and what was its volume yesterday. And so you know that when the volume is this, the price was that. When the volume was this, the price was that. For you go to a different day, a different pair of days, and you can do this. So you have labeled data, so you can calculate the predicted price versus the actual price, and that's called the error, E. Or you can call it whatever you want, but it's simple to call it the error. And then we define this function. It's called the cost function, which is Y minus Y hat, so it has the error in it. But if you think about this calculation, Y minus Y hat, sometimes it's going to be positive and sometimes it's going to be negative, right? Sometimes this is going to be bigger than this. Sometimes this is going to be smaller than this. So it's going to be positive and negative. And we're going to want to sum up the error for many examples of our data, or many instances of our data. Like in the stock case, we're going to do we're going to look at the relationship between volume and price for maybe 1,000 days. So we have 1,000 past instances, and we're going to do this calculation for all of them and sum them up. Now, if you get positives and minuses, you're going to get a lot of cancellation, and that isn't really a good measure. If you allow cancellation, it could even get 0. That's not really a good measure of the error of your predictions, right? So that's not really what you want to do. You don't really want to get that kind of cancellation. So we have a couple choices. One is we could just take the absolute value of this. That would get rid of cancellation when we sum it up. So we'd have this, right? We'd have Y minus Y hat, and that would get rid of it. But if you remember in high school or junior high school, when you do math with absolute value signs, it gets pretty awful. It's not so clean. So we don't really want to do that. So instead we use squaring. That also gets rid of the cancellation. And then we throw in this extra 1/2, and that's just because we're going to take the derivative of this. And when I take the derivative, so I'm going to want to take dj d y hat. Okay, so if I want the derivative of that, so what is the derivative? If this is with, or just let's say with this expression, not with the 1/2. So what's the derivative of that? Can somebody tell me what that is?
That will be 2 times y minus y half.
Right, good. So it's 2 times y minus y hat. That's right. And that's fine, that's good. But the thing is, we're just going to use this j for comparing, like how much cost or error was there when we had one model versus how much cost was there when we have another model. So if I take out this 2, it's not going to really matter, right? Because I'm just using it to compare costs between models. So, you know, if this cost was, sorry, for one model, the cost was, so I'd have like a particular prediction, you know, so we'd have an actual value here, and then y minus that and multiply. Anyway, since I'm only using it for comparison purposes, I don't really need this extra factor there, because they're both models will have the 2 in there, so it's going to make whichever one was better is still going to be better, whether I leave the 2 in there or I take it out. So we don't really want that 2 in there. So we define the j by 1/2, with 1/2, sorry. So then it's 2, but there's also a half there. So it becomes 1. So that's the only reason. It's not necessary. It just makes the answer cleaner. So it makes the answer just that. So that's the only reason we put the 1/2 in the front. Okay, and as I said, if we're just using this to compare which model is better, whether we use 2 in both cases or 1 in both cases, it's still going to give us the same answer as to which one is better. Okay, then we can take the y hat here, and we said that y hat was equal to this, so we can put, instead of y hat, we can put this there. Now, I made a mistake here. I forgot the 2. That should have a 2 there. So that's a misprint here. And yeah, but anyway, other than that, that's what we have here. And then we can just do some sample calculation in R, where we just fill in an X, a W, and I guess that's all we need. An X, I'm sorry, an X, a W, and a W2. An X, a W1, and a W2, if we just predefine those. So X, W1, W2, and we have a Y hat. I'm sorry, we have a Y. So we have this Y. Suppose we have that also. We can just do a sample calculation by doing all these steps and just getting out some number at the end for our prediction. Okay, so, and this J is called the cost function. Okay, it's called the cost function. Okay, and we can build the cost function also. So here's we write the cost function. We're going to allow for an X value, a W1, a W2, and the Y value. So the user will be able to supply these. And then once they supply these, the X value, the W1, the W2, and the Y value, we return the J. So here's the calculation, and we return that. So if we put in these previous values, here, x1, x2, x3, and y and y. We get that. Why don't we get the same thing here? I don't know. That's strange. What did I do wrong? I guess I didn't use the same values. That's kind of weird. Oh well. Must have used a different x, w1, w2, and y to get this. Okay, anyway, now we write the same thing for this network, where we said now we're going to calculate the only difference between this network and the previous network is that to get Z2 in the previous network, we did this times this, and now for this one, we're going to do, to get Z2, we're going to get this times this plus this times this. So that's the only difference in the calculations. And we can, now we see that in order to get this calculation of Z2, we can treat this as a vector and this as a vector. So we have a vector like this, x1, x2, and we have a vector like this of w1, w2. And we see that if we just take the dot product of the two of them, we get the Z2 that we're looking for. So we can use the dot product in that case to get this. Now we can also call these matrices instead of vectors. And in that case, the matrix product will also give us the same result. So if we do this and this, now this is a 1 by 2, and this is a 2 by 1, so we're allowed to multiply these two. And when we multiply them, we get a 1 by 1, and that will be our Z2. Okay? And so we can do that. So we can say that the calculation is the matrix X times the matrix W, and other than that, we still have the, we get a cost function. And then we can write this here as matrices. So we start out with here's X. So X is a vector. So we start out with a vector X, and then we convert it to a matrix like this into a 1 by 2 matrix. And I think we did something with W. Yeah, here's W. And we do the same thing. We convert it to a matrix like this. And then we can run, and here we're going to define these variables, the input layer size, the hidden layer size, and the output layer size. So in this example we're doing right now, the input layer size is 2, but this layer size is only 1, and this layer size is only 1. So we have 2, 1, 1. But when we define these, hopefully our code will be written in such a way that we can change the size of these, just change them up here, but the code will still run the same way. So then we can have an input layer size of 100, and we can have taken 100 variables. We could have 1,000 hidden layer nodes. So all we'd have to change is 100 here, 1,000 here, and leave this the same. And then we'd have a completely different network, but everything will still work the same way. Okay, so we're going to define these variables, and hopefully we're going to use them so that, for example, the X matrix is going to be 1 by the input layer size. So now it's 1 by 2, but it could be 1 by 100. And the W1 matrix is going to be maybe the input layer size. Oh yeah, like 2 by, is this right? Is that wrong or right? Yeah, that's right. Okay, so that will be the input layer size. Okay, so and then we have our code, and we can so that we can calculate the we can do a calculation for the J cost. We're calling this J cost for 2 inputs. Okay, and we can also run this without any arguments if we want, as long as these have already been defined somewhere, and then it will run. But normally you wouldn't do that. Okay, now we've talked about this, I think. We talked about this. This is the weight matrix. And we have the indices here. So we know, for example, what does this mean? Can somebody tell me what that means? Can somebody interpret the indices here?
That's the weight from x2 to the third node.
Right. And what's this one mean?
The one is like the first layer.
Right.
First
Okay,
layer.
good. Right. So so that's the interpretation of this. But actually, there's another interpretation, and that is it also tells us where in this matrix it's going to be. So he's right that it tells us that it goes from 2 to 3, but it also tells us what row and what column it is in. So the weight that goes from 2 to 3 will be where in the matrix? It will be in the second row and third column. Okay, so we have both. The indices tell us both in terms of the layout of the architecture, where the weight it goes from where to where, but it also tells us in terms of the layout of the matrix where it goes in the matrix. Okay, so we can read it in both ways, or we can understand two things from the indices. Okay, and now we see that our calculation for Z2, when we're doing this layer, we already said it for Z21, for this layer, for this architecture, or we already said it's this times this, and this times this. Again, we already said it, but it's that times that, and that times that, and we add the results to get this. So now we have these, we've defined two matrices, the input matrix and the weight matrix. And this one is going to be a 1 by 2, and this is going to be a 2 by 3. So we're allowed to multiply them. And when we multiply them, we'll get a 1 by 3. And that's what we want. We want a 1 by 3 because we want to get this, this, and this. So we want to get 3 different elements. And a 1 by 3 will give us space to have 3 different elements. This is what we want to get. So we'd like to, it would be great if our multiplication would produce this. Then we could write, if we could find a multiplication that would produce this, then instead of writing all these equations, we could just express everything as one matrix equation. So that's kind of nice. So if we could do it, it'd be nice. Otherwise, of course, we don't have to do that. We can just say this is the calculations. But it would be nice if we could somehow express it as a matrix multiplication. And it works out perfectly, just like this. If we just put this here, and we matrix multiply, it just works out just like we wanted. Because the first element, Z here, Z21, is what? Is this one. We need that, but we can see that that's the dot product of what? Of x1, x2 times w11, w21. Well, when we do matrix multiplication, that's exactly what we get. When we multiply this matrix times this matrix, we take this times this, or this times this, and we do the dot product of those. That's what matrix multiplication tells us to do. Take the dot product of this times this to get the first element. It says take the dot product of, pardon me, this times this to get the second element. So the dot product of this times this, here times here, is exactly this. That's exactly what we wanted. So it kind of just works out that we can say that we can express the whole Z2 here as just, I guess I should have written Z2 equals that, equals X times W1. Okay? So it gives us just the thing that we want. So now we have a nice expression for the entire set of calculations for the Z at the Z layer, at the Z2 layer. Okay? Okay. And this is just a picture of what the matrices look like. So this one is a 1 by 2, and these weights are 2 by 3. And then when we multiply a 1 by 2 by a 2 by 3, we get a 1 by 3. So the Z matrix is will look like this. It won't be a column matrix, it'll be a row matrix. And then A2, we just take each element in here and put it through the sigmoid function. So we just take f of the first element. F is, we're denoting the sigmoid function by f. We don't use sigmoid usually. We can, but we don't often use sigmoid because actually we don't have to stick with the sigmoid function. There are various other functions that are used instead of sigmoid, but they're all nonlinear, and that's the key. So we'll just call them f in general. But usually for our purposes, for the first 2 or 3 chapters that we look at, they are the sigmoid function. So anyway, we put this element, this is Z, this one here, into F, and we get this. We put this one into F, and we get this. So we take this into, and we get another A, which is also of the same shape, A2. And then I guess we might take so this is what, 1 by 3, and this is 3 by 1. So here's the weight matrix. Here is a column matrix in order to make this multiplication work, and we end up with a 1 by 1. So this is just a picture of it. Okay, now we want to write it all using the matrix calculations because that makes it simpler. So we define X, we define X into a matrix, we calculate Z2 as X times W1, and this is matrix multiplication operator in R. So we can do that now. In Python, you probably have, there's probably a different, if you use, what is it, pandas or NumPy, I forget which one. You have a different operator, but whatever. This is the operator for matrix multiplication in R. So it's percentage star percentage. So we do that and we get Z2. And Z2 is just like we hoped. It has 3 elements in it. Okay, then we put Z2 into F. And now why is F bold here? Why is that bold?
It's a vector value function.
Right. It's a vector valued function. Well, why is it a vector valued function? Well, we're taking, what's the input? It's the Z3s. And what's the output? It's the A2. So we're getting a whole vector out. So, so it's vector valued. We're getting a vector out. So that we in our previous chapter, we said that when you have that scenario, when you're getting a vector out, we're going to make it bold. So it is bold. So it's like this, and the result is like this. So it's f of the first one. Now this is not a bold f of the first one, and this is not a bold f of the second one, and so on. So we get, but this is a vector at the end. So we do get a vector out, or a vector as the result. Okay. So we can write A2 equals that. Okay. So we can, and in R, you know, you can define a function, and you don't have to say it's going to be, it's going to take in a vector, because every function in F takes in vectors. Now, I don't think that's true in NumPy or pandas or whatever, but in R, any function you write can have as its input a vector, and this has the Z vector, or sorry, Z matrix as an input. And you can do that very simply in R. You don't have to do anything special. It'll just take that and it will work. Okay? And it returns a vector as well here. So, or rather here. It returns a vector here as well, because this is a vector, so this will return a vector. Okay. So, and then we do the same kind of thing for Z3, so you can work it out. You can read through this. We're going to calculate Z3, and it's going to be, and then we're going to take f of Z3 to get y hat. So you can go through this, the same kind of stuff. Okay, here we talk about why the sigmoid function. So we already talked about that because it's not linear. And there's something called the universal approximation theorem, which states that so whatever the relationship is between volume and price, so maybe, it looks like this. Maybe that's the true relationship between volume and price. Now, our data is not going to follow that perfectly, right? Our data might look like this and this and this and this. This is our data. But the real relationship, if we were able to get it, is the green curve. Maybe our data looks like this and that. But so our data is not perfectly that, but this is the true relationship. So we're trying to find this true relationship with our neural network. And if we were, as I said, if we were stuck with only linear functions, then we're going to be stuck with trying to approximate, for example, trying to approximate our data with just a straight line. So that seems very limited. But if you have if you include the sigmoid function in the as part of our calculations, then the universal function approximation theorem says any continuous function can be approximated by our neural network, as long as our neural network includes the sigmoid function. And I guess it depends. You have to have enough nodes for this to get, in other words, to get closer and closer to the true curve, you have to have more and more nodes. But you can get as close as you want to the true shape with the neural network, just by basically increasing the number of nodes and maybe the number of layers. But you can't do that if it was linear. Doesn't matter how many more nodes I include and how many more layers I include, I can't get as close as I want to this green curve, right? Obviously not, right? You know, what am I? I'm still going to be stuck with a line. It's never going to get very close. Certainly not as close as I want. As close as I want means infinitely close, basically. So I'm never going to get infinitely close to this curve with a line. But if you have the sigmoid curve in there, sigmoid function in there in the calculations, the universal approximation theorem says that you can get infinitely close to this. Infinitely means as close as you want. Like you can say, I want all the error to be like less than 0.2. You can do it. I want the error to be less than 0.02. You can do it. I want the error to be less than 0.0002. You can do it. But you can never do that with this blue line here. Okay? So that's why we have the sigmoid function. Okay, now. All right, so now we have discussed what is called the calculations going forward in the neural network. So you put in X, you do blah, 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 and you get out Y hat. So that's called going forward in the network. And that is called forward propagation. Do I write that? I don't have something to type right now, so I can't really, I don't want to write that out. But it's called forward propagation. Okay? So we've discussed what's called forward propagation. Now the thing is, we're just going to make a prediction based on all of this. Now, the thing is, we didn't mention it, but the weights are initially randomly assigned. So these weights here, these weights, and these weights and these weights are all randomly assigned at the beginning because we don't know what else can I do, right? I need weights, and I don't know what weights to put in there that are going to give me a good prediction. So I just have to fill them in with something. So that sounds pretty bad, but we have a learning process which will tell us how to adjust the weights afterwards. So anyway, but at the beginning, we just have these weights that are randomly assigned. Now, usually we randomly assign them between numbers between 0 and 1, but still they're randomly assigned. And I guess they don't even have to be between 0 and 1, but it turns out that might work better. But so we're going to each one of these is going to be a random number between 0 and 1. So we assign them randomly. But then the thing is that obviously that's not going to give us a particularly good prediction, right? Like if I'm trying to predict the stock price, and I assign these weights randomly, there's no reason to think that I'm going to get a good prediction of the price, right? It's just a bunch of random calculations. So no reason to believe that it's going to be good. So we need some way to improve it, which means we need some way to, and in terms of what we can change in the network, we can't change the X's, that's our data. We don't get to change the data, right? We don't get to change the prices of the stocks, in the past, the price and the volume, we don't get that, right? We just have to look at the prices and the volume and then, try and predict for the next one. We don't get to change that. And then these Z1, Z2, Z3, and this, those are all determined. Once you know what this is, and once you know what the weights are, then these are all determined. These are all determined. Then these weights are, if you have the weights, then these are determined and these are determined. So there's nothing that we can change here. We can't change the X's. We can't change these. The only things that we can change are the weights. So, so in order to improve our prediction, we have to change the weights. Now, changing the weights sounds like a good idea, but knowing how to change them doesn't sound like a good idea. I mean, how are we supposed to know how to change these weights in order to get a better prediction? Like suppose we have a bunch of weights here, here, and the stock price yesterday was 100, and the volume was, 5 million, okay? And we put in all this, and we get out a predicted price for tomorrow of 120. Okay, great. So, and the actual price was, say, 100, say 105. So this was the real price. I'm sorry, so we wait until tomorrow, and we find out that this was the actual price, and our prediction was this. Okay, so how should I change these weights? Does anybody have any suggestions? Well, obviously it's not very simple, right? It's like you don't know how to change these weights, right? It's just too complicated. We might say, well, maybe these were a little bit too big. And maybe the weights were a little bit too big because the calculations gave me 120 and the actual price was only 105. But, after saying that they're a little too big, then what do I do? I have no idea how to change these. Well, maybe I could change all of these, by 1%. So reduce this by 1%, reduce this by 1%, reduce them all by 1%, and maybe that's going to make it better. Well, yeah, that's possible, but it's really messy. And there's like no, you'd have to just keep testing, many different configurations of weights, and that seems like an impossible task, right? So it's not so clear what to do. So, but this is the problem that the guys who started working on this in the 1950s and 60s, they thought of making neural networks. They modeled them on on a brain, probably a brain of a mouse or a cat, but also, of course, on a human. And so, they were wondering, like, how does the human brain learn? Well, maybe there's those sort of connections between neurons in the brain, and they fire, and sometimes they fire and sometimes they don't fire, depending on what's happening. And firing means like something comes out of here, and then some way it gets attenuated. So that's what the weight does, is sort of modify how much is fired, and then the result goes to the next node, and then the next node sort of processes it and gives it this, and then that fires, or maybe it doesn't fire, and then this kind of modifies it, and then so they're thinking that's the way it works. That's the way the brain works. So but anyway, then how does the brain learn? So it does this, and so you're, for example, you're looking at something and you think it's a cat, but it's actually not a cat, it's like a flower, right? So your brain has to learn that. So you walk up to it, or a baby goes up to it, and it's not a cat, it's a flower. And then the baby's sort of learning. So how does it learn? What happens? So we're saying that these weights in this model, we're saying that the weights are changing, but how? How does the weight change, right? So that's the problem. How do we change these weights? Okay. Well, we don't know. We have a big problem, and they had a big problem. They had no idea what to do. They start just playing with a very simple network, like maybe they go back to the other network architectures that we had, and they just have, let's say, just a 1, 1, 1. Then it's not so complicated. Then maybe you can sort of make guesses about what you should do. but it's still not straightforward at all. So that was the big issue. How does this network learn? So, does anybody have any suggestions on what we can do? Or any ways to think about this? Or any, imagine you're sitting there in the 1960s and you have this idea, oh, I think this is pretty good, blah, blah, blah. But now you come, oh, how am I going to do this? And who knows? Anybody have any path forward? So, these guys are sitting there for weeks and weeks and months and years, trying to hope that, they're coming up with something good here, something new, but they don't know which way to go. They don't know what to do. Well, there's some mathematics that they can take advantage of. And we've learned that mathematics. So what we're thinking is that the error, J, of course, do we want to make J bigger or smaller?
Smaller.
You have to unmute yourself.
Smaller.
Smaller. So we want J to be smaller. And so now, and also J is a function of the weights, right? J is a function of the weights. Does everyone agree with that? Does everyone agree that J is a function of the weights?
Yes, Professor.
Okay. So let's make this really simple, because if you think about it in terms of all these weights, you can't think of it. So let's make it really simple. Let's say there's only one weight. Now, there's never going to be only one weight. In the very simplest network, there's going to be two weights, right? Going all the way, well, I'm not going to go back, but the 111 has two weights. But anyway, let's just make it even simpler. Just for thinking about it, let's just suppose there's one weight. So that would mean J is a function of W, means that we can think about a JW plane. So this is, thinking abstractly about the problem that we have, right? Because this is, we're thinking about this, but suddenly we move to this JW plane. So I can say that's kind of thinking abstractly about the problem. But anyway, we can think about a JW plane. And what we're saying is, depending on W, we get different costs, right? If the weight is one thing, we're going to get a certain error. Maybe we get 120, and if we change it, maybe we'll get 115. And if we change it again, maybe we'll get 200. So anyway, the cost is a function of the weight. So there's some curve here. Now I'm drawing it like this. It certainly doesn't have to look like that, but I'm just, trying to make things simple, because the simpler we can make things, the better we can get some kind of insight. Now, of course, the insight might need to be modified as we make it less simple. But if you just start with thinking about not just one weight, but 10 weights, you're not going to get any insight. So it's better to make the problem as simple as possible and be able to get some sort of insight. So that's what we have here. And then I even made the curve like this. So even it's even more simple than if the curve looked like this. Right? We're not going to look like that, but right? So I'm just trying to make it simple. Okay, so suppose it looks like that. Okay, now we have math for this. So what are we trying to do? Do we want J to be big or small? We just said we want it to be small. So, and what can we change in our network? We can only change the W. The W's, or in this case, we can only change this W, one W. So let's suppose that we have, we start with a random W. Let's suppose it's right here. Let me use this, W0. So suppose we have that. So what can we do? Well, we could say that we might say that we were thinking about this. We might say that. So we might say, well, I think that as I change W, I can change J, right? So when you put it into this, in terms like this, which is not, not such a natural thing to do for most of us, but for maybe somebody who's playing with math all the time, maybe, changing the question to this symbol is not such a big thing to do. And so they focus on this symbol. Now, and also on this picture. So what did we learn about this picture and this symbol? So what are we trying to do? We want to improve J, right? We want to make J smaller. So what does that mean? We want to adjust the weights so that J in this picture is lower. In other words, we'd like to find this weight right here, because that's, according to this picture, the best J, the lowest J. So we'd like to find that point. Once we got to that point, that would be the weight that we would set things at, and that would give us our best prediction. It may not be a perfect prediction, but it's going to be the best prediction. Okay, so we'd like to find that W, this W here. Let's call it W best. Okay, so what can we do? Now we know stuff from chapter 9 and chapter 10. So what can we do? We did do chapter 10, didn't we, in this class?
We set it to 0 and like solve it like a
okay, good.
minimum.
Perfect. Right. Okay. So yeah, we could, like you said, take the derivative of J. So J is going to be a function of W, right? Going back to the simplest one, we had some equations, right, for J. Where were they? Right, we made sure to say that J was a function of, here, by the way, this is also missing the 2. Okay, so we had this equation that says J is a function of the weights. Now this is the matrix equation, but we had something up earlier where it wasn't matrices, but it looked the same. So J is definitely a function of the weight and the weight. Now I'm saying let's just talk about one weight. So this is not exactly the equation we have, because I'm just making something up to make it as simple as possible. So I'm saying, let's suppose we didn't even have 2 weights. So let's suppose we didn't have this weight. So we only had this one. So anyway, but J is a function of that weight. So if we want to make J small, he said, take the derivative of J with respect to W. Sorry, That was wrong. Oops. Sorry. Okay, let me try that again. J with respect to W and set it equal to 0. We know that trick, right? You know, suppose this was J equals X minus 10 squared. And you want to find the derivative of this with respect to X. So what is that? That's 2X, just 2X, right? That's 2X, right? Yeah. No. 2X times X minus 10, I think. Is that right or not?
I think there's no X outside of
Sorry, there's no X, right? Sorry, not thinking. Okay, so it's 2 times X minus 10. So, okay, so that's the derivative. That's J prime. And then we set J prime equal to 0. And we find out that X is 10. So X is 10 is when it's lowest. So, okay, so we found that when the X is 10, that's where the curve, whatever the curve looks like, is going to be lowest. So we could do that. Great. We all know that trick. That's from first semester calculus. That's great. But the problem is that doesn't quite work here because we can't, our equation is not nearly as simple as this picture. Remember, it has the sigmoid curve in there as part of the equation in reality, right? Right? It's not like this, not so simple like this is. So it has the sigmoid curve and all this other stuff. So, but still, we actually can find the derivative. So we're not saying we can't find the derivative. So even though the J here is going to be pretty complicated, we'll still be able to find the derivative actually. So we'll still be able to find J prime, but the derivative is not going to be so simple like this derivative. And you might say, well, I can always find, you know, no matter what the derivative is, if I want to set it equal to 0 and solve, I can always do it. But it's not true. It's not always easy to set it equal to 0 and find the X. Here, I set it equal to 0 and found that X was 10. But for a complicated equation, even if I find the derivative, so I can get this part, but setting it equal to 0 and solving is not going to be easy. In fact, it could be impossible. So we can't do that. We can find the derivative, but we can't solve the equation where we set the derivative equal to 0 and find X or find W. We're talking about W, not X. Here we're talking about X. The variable here is X. Here the variable is W. So anyway, but still we can't set the derivative equal to 0. So, big stuck. We're really stuck. Well, fortunately, mathematicians have developed other methods for finding where the point is lower, the value where the curve is lower. People started, did some work in the 19th century and maybe even later than that, and they had other ways to do this besides taking the derivative and setting equals 0, because that just turns out not to be. This part is okay. We can do this. Sort of surprising. That part we can do, but just setting equal to 0 and solving is the hard part actually. So we can't do that. So we need some other way. So anybody else? Some other technique.
the gradient descenting.
Right. We talked about gradient descent, right? in our class, didn't we? Everyone?
Yes.
Okay. So we talked about gradient descent. So what does it say? It says that if you're over here, if you're over here, W0, and you want to get to W best, you can do what? You can find the gradient or the derivative at that point, and then you'll know whether to move to the left or the right. So how do we know whether to move to the left or the right? Well, here, which direction do I want to move?
To the left.
To the left. Now, what is the slope of this curve? I'm sorry, is the slope of this curve positive or negative? The slope of the tangent line. Is that positive? It's positive, right? And on the other hand, suppose I was over here, some other W sub something else, let's say W sub A. Suppose I was there. So if I go up here and I say, what's the slope of the tangent line here? In other words, what's the derivative there? Is that positive or negative?
Negative.
Okay. So when the slope is positive, which direction do I want to go?
Left.
Left. When the slope is positive, which direction do I want to go?
Left.
I'm sorry, when the slope is negative, which
Right.
direction do I want to go?
Right.
Right. Okay. So the derivative does, and you can see, or you can check it, that's going to be true whenever it's negative. You're always going to want to go to the right. And whenever it's positive, you're always going to want to go to the left. So that the sign of the derivative tells you whether you want to go left or right. So that will define what we should do. So if we can find the derivative of the function, if we can do the derivative part here, then we just check the sign. If the sign is greater than 0, that means the red line, then we know that we want to change the weight by subtracting, or we want to reduce the weight. So if the sign is positive, like this situation, then we want to reduce W0. And if the sign of this is negative, then we know we're here, we want to increase W. We want to increase W, right? Does everyone agree with this algorithm? Does everyone agree with this algorithm?
Yes.
Okay. So that's and that's what that is what gradient descent tells us to do. It says take a look at the derivative and then move according to what the derivative is. So that's what we're going to do. And then we move. So maybe we were here and we move to here. And then we do the same thing again. Okay, we're here. Which direction should we move? So we find the slope is that. So the slope is positive. So we should move again to the left. And that is the gradient descent method. And we just keep repeating that over and over again. And we get, hopefully, closer and closer to the lowest point. And each time, hopefully, we're improving the network. We're improving our predictions. We're getting a lower error, a lower J. Okay, does everyone follow this? So let's say that we started with a weight of W0. Now, what do we do? Now, if the derivative is positive, like it is on this red line, do we want to, let's suppose we're going to, I'm sorry, suppose we're going to change, we're going to get a new weight, W new weight, somehow. We're going to move to a new place. Now, I only want to give you one of two options. You can either add the derivative or you can subtract the derivative. So I'm not allowing you, so I'm going to put the derivative here, and you have to choose between add or subtract. So I'm going to put dj dw here. Now dj dw is either going to be, in this case, it's going to be positive. In this case, it's going to be negative. So let's take this case when it's positive. So W0 is here, and the W best is here. Now, and the derivative is positive. So do you want to subtract the derivative or do you want to add it to move to a better place?
Subtract it.
You want to subtract it, right? Right? If you added it, you're going to be moving away. You're going to be moving this way, right? Because the derivative is positive, and if you add it, then you're going to move this way. So you don't want to do that. You want to move to the left. And since the derivative is positive, you want to subtract it. Okay, now let's see what happens. Suppose we're over here, though, at WA. Now, do we want to move to the right or the left? When we're at WA, do you want to move to the right or the left?
Right.
To the right. Okay, so now, but what is the derivative? Is it positive or negative?
Negative.
Negative. So do you want to add the derivative to this or subtract it?
Subtract it.
Subtract it, right? You still want to subtract the derivative because before you wanted to move to the left, now you want to move to the right. So if you subtract this, the derivative is negative. If you subtract a negative, you get a positive, which means you will move to the right. So this formula works for whether it's to the left or to the right. Does everyone agree with that? If you subtract the derivative, over here, the derivative is positive and you subtract, you're going to go this way. But over here, the derivative is negative. If you subtract, you're going to go this way. So it works both cases. So this works both cases. Does everyone see that? So to get the new value, we could use this formula. Now there's sort of one problem with this. It does move us in the right direction each time, but the derivative could be very big. So like here, suppose this slope is very positive. It's very steep here. Let's suppose, yeah. So and suppose this number was actually just a 2. So W0 is 2, and we want to get to, suppose this is just a 1. Okay, so we only want to go from 2 to 1. If we can go from 2 to 1, that's perfect. That's going to get us to the very lowest point. But suppose the slope of this line is 10. Right? It's this could be a very steep line. The red line could be very steep. So the slope is 10. So if I subtract from 2, W2 is 2, or W0, sorry, is 2, and I subtract 10, then I'm going to go all the way over to minus 9. I'm going to be all the way over here, minus 9. Now, that's no good. I don't want to do that. Right? I want to go maybe to here the first time, and then to here the second time. I don't want to go all the way over to here, right? So I don't want to be stuck with subtracting exactly the derivative. So we put an extra factor here of r. Okay, that's supposed to be an r. So that we don't have to subtract the entire derivative, because the derivative could be a very big number, and we don't necessarily want to move that far to the left. So we say, okay, we're going to put in r, and r could be like only 0.1. So then, even though the derivative was 10, if we only subtract 0.1 of 10, that's much better than subtracting 10. So this is actually our equation for how to update the weights. We start with our given weight. We calculate the derivative. We have some proportionality constant here, which we can choose before we start. So we might choose it to be 0.1 or whatever. And then we just run this algorithm. So we check the slope, and if the slope is positive, then we're going to subtract a positive number, and we're going to get a new W. And then we do the same thing again. We check the slope, and if the slope is still positive, then we're going to move to the left again, and so on. Does everyone follow this idea? So this is our scheme for updating the weights. So we just keep repeating this scheme over and over again, and hopefully we'll get closer and closer to here. Now we might end up going, one time we're here, and then we end up going over to here. So then what's going to happen? Then we're going to have a negative slope. Hopefully we're going to move back to the right. Okay? Now, we may never get to the actual lowest point. We might end up bouncing from here, back then to here, then back to here again. Maybe it's possible. We keep bouncing and bouncing and bouncing, and we never get to a lowest point. But that just means that we didn't, the network is not completely optimized. But it doesn't mean that we haven't gotten a good neural network that can do good predictions. It's not perfect, but it could be good. Okay, and the same thing here with the R. How do we choose a good R? Well, we choose, say we choose R equals 0.1. And then we run this neural network, we run this algorithm over and over and over again, and we get to a certain cost. And we can't seem to improve the cost past that. Okay, then, so now we can use our neural network to make predictions about new data. Like suppose we're trying to design something to drive a car without a driver, like a driverless car. So we'll have a complicated neural network with many, many, many thousands or tens of thousands of weights in it. But anyway, we train it. This is training it. We find the best set of new weights, and that's where we have. And then we can see, okay, now we have a car and it drives pretty well. So great. Then you could say, well, maybe I could improve this car by having chosen a different R at the beginning. So you put in a different R, maybe you choose R as 0.2, and you see how that performs. And you train it, you run this updating over and over and over again for the new weights, and you get some other cost function, some other cost result. Maybe it's better, maybe it's worse. Okay, then, if it's better, then you say, oh, now I'm in better shape. I can drive more safely. If it's worse, no, then I'll go back to the other one. And then you try, okay, maybe I'll try a different R and see how it works. So you can just keep checking different R's to see, what gives you better performance. Okay, so that's the way we play with these things. Okay, so, but anyway, this is what we call the update formula. This is how we start with a given weight, W0. We subtract this from it. We get a new weight, then we do it again and again and again and again and again. And we keep improving, hopefully, the the performance or keep reducing the cost. But like we said, we might end up finally just bouncing around and never really getting any further improvement. But still, we have maybe a reasonably good performing network. Maybe we can predict the stock market. We can make billions of dollars in 1 week, which doesn't sound very realistic, right? If you could do that, you'd be rich. There'd be a lot of rich people. Maybe there is somebody who figured out how to do it and they're not telling anybody. But anyway, so this is what we have. Okay, so this is the update formula. And we're not going to do this, we're not going to just have a situation where we just have one weight. We have more than one weight. Here we have all these weights and all these weights. But we use the same idea. Now, so what was very key here was this. Right? Does everyone agree that that's key? The derivative, right? The derivative was key. Now, I was doing it for a super, super simple network. In fact, my network only had one weight, W. Now that's not, we never have just one weight. We have to have at least two weights. So if we have two weights, then what's going to happen? If we have two weights, so let's go back to here. Not going to be quite as simple anymore. We tried to make it as simple as possible because we can't think about non-simple cases, at least at the beginning. But here we're going to need to adjust this and this. Let's just think about this though. So what do I want? First I want dj d, so I'll call this dw2. So let me just call it dw2 like that. That doesn't mean square. I just don't want to write the brackets. Okay, but what is j? J is, this is kind of not such a simple thing. J is I don't have a good, let's see. Oh well. Okay, I'll have to write it out, which I did buy a new writing pad, but I haven't set it up yet. But anyway, J is what? It's, well, we can say it's y minus y hat squared and then 1/2. But what is y hat? That's 1/2. What is y hat? Because I need this j in terms of W2. Otherwise, I can't do a derivative. So I need y minus what? Y hat was what? It was f of z. F of z, what I think is z3. So f of z3 that was y hat, right? Y hat is f of z3, but z3 is what? Z3 is W2 times A2. So I get y minus f of Z3 is what? Z3 is A2 W2. A2, it's not A squared, that's A2 W2. This is not W squared, it's W2. And then squared, and then 1/2. So that's J. So I need D, J, D, W2. This W2. So I have to do the derivative of this. So what do I need? What math tool do I need to do this? I want the derivative, but there's a certain derivative tool that I need.
Chain rule.
What do I need?
The chain rule.
Yes, I need the chain rule. Now, in the assignment for next week, for the preparation for the test, I said you should go through a certain page on the chain rule. You need to know the chain rule clearly. You need to know what's in that page. Anyway, I need the chain rule here because this W is embedded in this function. So that means I need the chain rule. And then this function is embedded in this calculation. So that means I need the chain rule again. And then this calculation is embedded in this calculation. So that means I need the chain rule again. And then this calculation is embedded in this calculation. So I need the chain rule multiple times. Okay, in order to calculate this, which is what we obviously want this because we said we're going to use this to update the weight, right? We just made that formula with the R in it and the derivative and the old weight. And we said subtract and we're going to get the new weight. So we need it. We need the derivative here. But here, if I want the derivative, I have to use it's not as simple as I need the chain rule. So you need to understand, you need to work with the chain rule to get the answer to this so that we can update the weight. Okay, so you need that. And then we're not only going to need to do it for W2, because we're also going to have to know how to do this one. So we're going to change this one as well. According to, we're going to use this. So W1 to change W1. So you're going to need the chain rule again. And this one is kind of further away from J. Here's J out here. So to go from here to J, or to write J in terms of this, it's going to be embedded in more calculations than even this one was. So that means you're going to need more uses of the chain rule to get this one. So that's what we are stuck with. So we have to write all of this first mathematically just to see what it looks like mathematically. And then we have to put it in code. We want to write an equation for the updating. Where's the equation for the updating? Here. We want to write an equation for the updating that's this. We need this to write the equation. And so we're going to look at it, do it mathematically first, figure out what this is. But then we want to write it in code. We want to say, write some, say, okay, the new weight, going to change the weight in our code. And we're going to use it, do it by starting with W0, our original weight, our given weight. And then do this stuff. And we have to write an expression for this in math. And then we need to turn that into the code. And then we're going to, write this equation in code. And then we're going to update our weight. And we're going to get the new weight. And we can do it for each weight, for all of the weights, actually. And we can write, and once we get this, we can actually write it as a matrix equation, just so it looks kind of simpler in some way. And we can also translate that matrix equation into code. So again, it looks kind of simpler. And then we'll have the whole code for updating the weights. And then we'll just run that through a loop. We'll do it for each example. We'll update the weight once. So if we have 1,000 examples in our data set, in our training set, we'll just repeat this thing 1,000 times. Each time, hopefully, that will give us a better new weight. And so once we run it through 1,000 times, we hope that the cost J will be small. And we can check the cost J. We can check the cost J at any time, for any given set of weights. We can see what is J, and then we run this again, and we get a new set of weights, and then we can check J again, see how it's doing, and hopefully J will be decreasing, and that means that our predictions are getting better. And then we have the neural network. That is the neural network. So we talked about the feed-forward process today at the beginning of class, which is just, how do you go from putting these in? If you have a set of random weights, what's the prediction? But then we said, well, that's not good enough, though, because our prediction could be like this: 105 versus 120. It's not very good. So can't we learn from this 120? And now we've come up with a way, because we put the whole problem in terms of this J picture, the JW plane, and we realized that we have this thing called gradient descent, which can help us to improve the J's, and we can, and that will imply a change in the weights by this equation. And so we can change the weights and keep improving and improving and improving, and that's called learning. And then we're learning by changing the weights in an intelligent way. Intelligent means using gradient descent. And when we talk about gradient descent, we need the derivative. And when we need the derivative in a complicated function, we're going to need the chain rule. So anyway, we get the derivative, we update the weight, and we keep doing that. And that's it. That is deep learning. That is neural network. Then you just have to write it all out. You have to write it out mathematically. You can try and write it with matrices. Kind of makes it look cleaner, although putting it in matrices is kind of a headache. And then you have to write it in code if you actually want to use it. You can't just do it with math. Math just, you could just do it in math, but then you'd have a lot of writing to do. Every time you wanted to update, you'd have to go through the math equation. So you don't want to do that, because you can just write it in code, then you can just put it in a loop. Then you don't have to do anything by hand anymore. You just put it in the, the computer will do all the calculations for you. And you just run it through a loop. A loop meaning each time you get a new, you take a new data and you run it through. And so the loop is one iteration of the loop for each piece of new data. And then you don't have to do 10, 100,000 million calculations. You just let the computer do that. And you end up, yeah.
Can I ask a question?
Yeah.
Yeah, like in the case like where the, like the dj by dw curve, like when it has like two low points, like the graph.
Yeah, okay. Yeah, that's a good, excellent question. Yeah, so he's right. So you could have a situation like this. So you have a curve that looks like this, like that. So you're over here at W, 0, and you use the gradient descent, and you go over to here, and then you go over to here, maybe go to here, then you go to here, then you go to here, then you go to here. Oh, I got there. It's great. I found a low. I'm not going to go anywhere else. I'm going to find this. But over here, it's much lower. But you're not going to find that. So yeah, you could get stuck here. So you wouldn't have the so-called optimal performance. So maybe your car would, hit some people sometimes or something like that, right? So it wouldn't be so great, maybe, or maybe it would still be good enough. Maybe you wouldn't hit people, but you might not find this one. Okay, so that's possible. That's possible. Of course, it's not desirable. It's not the best, but it might be good still. But there are ways to improve on that, because remember we started over here at W0, right? So if we start over here at W0, we might only find this minimum here, this point here. But then you could just do the whole thing from scratch again, but choose a different W. Remember, W sub 0 was randomly set. So you might choose a different one. You might choose this one. Okay, here you might still end up with the same point over here as the lowest point. But then you keep doing it again. You choose a different random W sub 0. So maybe you end up here. Okay, still you end up here. But then sometime you might choose a W sub 0 over here. And then you might get to this point, which means your cost is much lower. So you can compare, well, which is the cost lower here when I got to this point or at this point? So you just keep running it again, but randomly choosing different W's at the beginning, and maybe you'll get a different, better value. It's not methodical in a sense, but if you do that, you might end up with a better, so depending on how you initialize the W's, you might end up with a different, and I'm sure people have other strategies as well for how to, how you might find a lower point. Okay, so yeah, you do have those issues. They're not, doesn't mean things don't work well, but they may not work perfectly. Okay? Any questions about that? Okay, so that is the story of neural networks. Now what we have to do is just write them in code and do the math, and then we're finished with this chapter. The next chapter we just add in one little thing, and then next chapter we write it using a different style of programming called object-oriented programming. We write the same thing, but we just write it in a slightly different style of programming, or a different style of programming. Then in the next chapter, we add in one extra feature, which will improve the performance. And then in the next chapter, we really use object-oriented programming in the right way, so that we can make a neural network where we can easily add in many layers. Like here, the way we're doing it now, it's like to add in a new layer is going to be a big headache to the code. But we're going to write it in a very modular way. So all we do is we're going to have a function called add, and we're just going to say add a layer with 15 nodes, add another layer with 20 nodes, add another layer with 30 nodes. And it's going to be as simple as that to add in nodes. So we're just going to write in a much better programming sense this code. And then once we do that, then we're going to use we're going to build what's called a convolutional neural network. So that's where we're going. Okay? Anyway, so you can see that this chapter is the heart of the rest of them. So that's why we're having a test on this chapter. Okay, that's all for today. So we have a big test next week. The minimum it counts is 40% of your grade. If you don't do well on it, it still counts 40% of your grade. And if you do well on it, it counts 55% of your grade. Okay, that's all. So please go through all of the videos and then read the book completely, then answer the questions, then read it again. Otherwise, I could ask you, why is this Z not capital? And you have to be able to answer that. Why is this a matrix? Or, something like that, something really might seem small, but I want you to know everything at that level. Okay? Okay, that's all.
Thank you, Professor.